Good morning everyone. Welcome to One Concept Per Day portal. This is the second question of the series of the questions that we are discussing for the concept on reflection and refraction. So in the first problem we had already learned about what is refraction, what laws apply over here, and how do you apply the laws for a prism, and what happens to the angle of refraction over here. You've seen all this so far, right? And what happens to the different refractive indices of the different colors of light. So therefore what we have learned in the previous one is we have learned that the different colors of light will see different refractive indices, right? Which is similar to saying that the different colors experience different oppositions, okay, different resistances when the light falls onto a given medium. The color of light falls onto a different medium. Okay, now let us look at the second question. This is about the sound waves. And now one method of finding the position of fish beneath a boat is to find out a pulse of sound waves. Okay, and we do this by an ultrasonic method from the bottom of a boat, and time and how long the pulse takes to return as shown below. The speed of sound waves of water is 1500. Speed is given to you. Emitter is seen here, receiver is also been seen here. The time taken between the pulse leaving the emitter and returning to the receiver is 12 milliseconds. So T is given. Now what is this T here? It says the time leaving the pulse, between the pulse leaving the emitter and returning to the receiver. That means you send a pulse from here, this pulse goes here down, gets reflected here and comes back to this point once again. So this is your T down and this is your T up. So T down plus T up is equal to 12 milliseconds, which means the time taken for down wave and up wave should be the same. So I can now say T down should be equal to 6 milliseconds. Okay, we are deducing something. For what purpose? Let us see it further. Calculate the distance from the bottom of the boat to the fish. Bottom of the boat to the fish. So here what we assume is, we assume that the waves are traveling with uniform velocity. When we say traveling with uniform velocity, what can you apply? What equation of motion can you apply? You can say distance by time is equal to velocity, right? So what is the distance? Distance is nothing but the depth starting from here, from here to here, right? So therefore distance, we need to find distance divided by time taken. What is time taken? 6 milliseconds divided by 6 milliseconds is equal to, what is the velocity? 1500, which is already given to you. Many students make a mistake over here writing this as 12 milliseconds. Okay, don't do that. Understand the problem and then solve it. So therefore now I can now write D is equal to 1500 multiplied by 6 multiplied by 10 power minus 3, which should now be equal to, how much is it? This is I can now write this as 1.5 into 10 cube, 1500 multiplied by 6 multiplied by 10 power minus 3. This goes away. So I get the answer as 1.5 into 6, which should be 9. Unit should be meters. Thus the fish is at a distance of 9 meters from the surface of the boat. Okay, now let us move on to the next one. In order to find the fish using the method, the effects of diffraction of the fish needs to be minimized. The diagram shows the plane wavefronts adjacent to an obstacle. Complete the diagram. What is meant by diffraction of the wavefront? Now what's happening is, you send a wave over there. There is a possibility that the fish is somewhere over here. Okay, it is not at the bottom. Okay, it is somewhere over here and still there is water over here. Now what can happen is, those waves need not get reflected. It can just directly go away here. Okay, which means now what prevents it, or what kind of wave should I use over here so that it hits and reflects back? That means I should be able to see the reflection phenomena and I should not be able to see the diffraction phenomena, right? Diffraction, what happens? It can just bypass through the fish. It can just create a shadow over here and then pass over here. Okay, it need not get reflected. Okay, I should see through it. Now this question is about diffraction. Now we need to draw the wavefronts for this. This is for 2 marks over here. So how do I draw? So what happens? What is diffraction? Diffraction is nothing but bending of light around corners. So therefore one wavefront, see, the distance between these wavefronts are constant. What does it give you? It gives you the wavelength over here. Okay, when it comes here, it has to bend. Now how does it bend? It will bend like this. So the rays are now coming like this over here. This ray will just go like this. But at this point, one ray will go like this, and the other ray at this point will now go like this over here. Okay, and as a result of this, now when you get something like this, how do I draw the wavefront? See, the wavefront will always be perpendicular to the ray. Okay, the difference, the connection between, or the relationship between the wavefront and the ray is that if you have a wavefront like this, I will have a ray like this. I can also have a wave ray like this. I can also have a wave ray like this. I can have a ray like this. What is that I'm doing? I'm drawing a tangent to this surface and drawing a perpendicular, right? Perpendicular. And this, for this perpendicular, there should be a ray being drawn. See, the angle between this tangent and this ray should be 90. Here also you see, this should be 90. Here also, it should be 90. Here also, it is 90. So therefore, see, this is one ray. This is the other ray. This is the third ray. This is the fourth ray. This is the fifth ray. Now I have drawn rays for every point over here. Okay. So towards it, now what I will do, here also I'll write like this over here. Okay. Now as a result of it, now we need to draw the wavefront. How do I draw the wavefront? Just put perpendiculars here. 1, 2, 3. And here you see the perpendicular is not like this. It is perpendicular is like this over here. And here it is like this over here. And here once again like this. Draw once again like this. So that means I should draw a wave like this over here. I should draw a wave here like this, and this should be going like this over here, right? And this one should be, it should be like this, and it should be like this. Now again, here it's like this. So therefore, once again, I'm going to draw a wave perpendicular here, and I'm going to write like this. And here, it is in this way. I'm going to write like this over here. See to it that the distance is same. Okay, distance should not change. And then once again, this point and this point over here. So it comes like this, takes a turn like this, goes over here, and for this point, it takes a turn like this and goes like this. And for this point, once again, let me take up this point. So it goes like this and goes over like this. Okay, and maybe for this point, it is not straight, it might be going like this over here. And for this point, it might be going in a similar way. So this might overlap, and you might have a wave going like this slightly. And thus, okay, when it goes away from the cross section, it is almost a straight line. Okay, don't write straight lines because you get a ray over here, so you can mention like this over here. Okay, so this is the wave. So what do I look here? I look at this region. I look at this region, whether we have written it properly, whether it's converging like this. Secondly, I look at the distance between the two wavefronts. It should be the constant because in diffraction, wavelength is not going to change. Okay. And here you fill this up. Okay, so now this will get you 2 marks. So we can ask you anywhere, but okay, whatever kind of surface it could be a single slit, it could be a double slit, whatever it is, but the wavefronts should always be drawn in a similar manner. Okay, now explain why you would expect the effects of diffraction to be negligible when sound of frequency 60 kHz is incident on a large fish. Now the question is, okay, why are we applying an ultrasonic sound, right? You usually heard in a sonar, we always use ultrasonic. What is it? Ultrasonic is something like whose frequencies are very, very high. So why, if I use a 60 kHz, what will happen? So to understand this, first we know what is the velocity. Velocity is nothing but 1500 meters per second. It's already given. And this is your frequency. So let us find out the value of lambda. Lambda is V by F, which should be 1500 divided by 60 into 10 cube, which will now be equal to 1.5 into 10 cube divided by 6 into 10 cube. 10 cube goes away. 1.5 ones are, 1.5 fours are, which should be around 0.25 meters. Okay, what is 0.25 meters? It is around it is 1.5 ones are, 1.5 twos are. So there's 660 here, right? There's 60 here. So this is 1 by 40 over here. So this should now be equal to 0.025 meters. Okay, what is 0.025 meters? This is around 2.5 centimeters. Do you think a fish would be as small in the ocean? Okay, not in the tub that you have, okay, but in the ocean, do you think it will be around 2.5 centimeters? It will never be 2.5 centimeters. It could be a larger fish. If it is a larger fish, how much can it be? It can be something like the length of it may be around a 15 centimeter fish, 15 centimeter, 20 centimeter, 30 centimeter, bigger fish, right? When you have a bigger fish, that means the dimensions of the fish, what is the dimension of a fish? Dimension of the fish is nothing but length of the fish is definitely larger than the wavelength. Okay, diffraction effects are possible only when the length of the fish is nearly equal to wavelength. If at all, if you have a length of a fish to be somewhere around 2 centimeter, 2.2 centimeter, 2.5 centimeter, and so on, then what can happen? The rays that you pass over here, the sound waves, the ultrasonic waves, it will just pass through it. It will diffract like the way you had mentioned over here. Okay, but if you have a larger fish, it will get reflected by it and come back. So for doing this, you should definitely use the frequency which is given something like around 60 kilohertz. Now, if you want to ask a question like, what will happen if I use a frequency signal which is around 20 kilohertz or maybe 10 kilohertz? What is 10 kilohertz? 10 kilohertz is nothing but you can use it in your audible sound waves. The waves that we speak about is around 10 to 7 to 12 kilohertz. Okay, now what we will do is let us use it with 10 kilohertz. If I use 10 kilohertz wave, then the lambda would be 1500 divided by 10 into 10 cube, which will now be equal to 1.5 divided by 10, which will be equal to 0.15 meter. 0.15 meter. Okay. Now, what is the length of a fish? Length of a fish is around 2.5 centimeter. Sorry, it's around 20 centimeter, which is around 0.2 meter. Now, you see this wavelength and the length of the fish are nearly matching. So what will happen? The waves that you talk or the high intensity waves that you send across the ocean will directly pass through the fish, will get deviated, will get diffracted, and then pass away. So you will not get the reflection. Okay. So you understand how physics is very important, even when you want to determine the location of the fish, location of a shark, or whatever it is. You need to understand that this is very, very important. How do you do for a whale or a shark? What kind of fish, what kind of wavelength do you need? The lambda is very, very larger. Okay, for a whale, it could be around 2 meters or 3 meters, right? If your wavelength, if your length is very large, maybe around, let us say 3 meters, for example, is the length of a shark, then your frequency should be equal to V by 3, right? V by lambda. I'm just taking the length of the fish and lambda are nearly same. So this should be 1500 divided by 3, which should be around 500 hertz. Okay, 500 hertz over here. The frequency should be much more lower. Okay, so therefore you cannot use those kinds of frequencies. Okay, so let us continue with the next problem in the next video. Thank you.